Hello, everybody. Last time we talked about the deaths of lower mass main sequence stars, a star like the Sun, saw that they went through, they swelled up, became larger, became cooler, the outer part at least, and became giants, or red giants, depending on the color, orange giant, yellow giant, red giant. And then the planetary nebula stage happened after there was too much shell fusion going on around the carbon core, and then there was this planetary nebula stage, because it was the burp, the cosmic burp of the envelope into space, and then the core left as a white dwarf. Well, today we're going to talk about other stars, more massive stars. We're going to talk about upper mass main sequence stars. And to do that, let's make an HR diagram. So you should be pretty familiar with this. Good to know the HR diagram for quizzes, for exams. So let's do this. We have temperature, getting hotter. We have absolute magnitude. Let's talk about things we've already talked about. We talked about this region over here. Give you a few seconds. A place where stars are born, stellar nurseries. What is that called? Yeah, that is the emission nebula. But remember, those are not stars, not yet. It's not a star until these protostars end up having fusion go on in their cores, sustained fusion, and then we're left with, a star. We have a star. And what is this region? The main sequence. Remember, we also have this dividing line between the upper mass and lower mass main sequence stars. What does that line represent in solar masses? 10 solar masses. Very good. If you got it. If not, don't worry about it. Now you know. 10 solar masses. Anything over 10 solar masses, any star in the main sequence is an upper mass. Anything less is a lower mass. Sun, let's say, was right here, and it used to be part of the emission nebula. Now it's been here for about 5 billion years. Remember what we said it's going to do? It's going to swell up, and it's going to become a probably K-type star, but it'll be a giant. And remember what's going to happen to it? Eventually, planetary nebula stage happens, and the core that's left over is found here, which is a white dwarf. So this is what we talked about already. But today we're going to talk about this. Let's talk about a 20 solar mass main sequence star. Remember, it's 20 is the upper mass main sequence. So that's our title for today. We're going to talk about the deaths of upper mass main sequence stars and supernovae. So let's show the title here. So here we go. The deaths of upper mass main sequence stars and supernovae. So you should write that down. That's the title for today. We're going to see what happens to these stars, which is much more dramatic than what happens to a lower mass main sequence stars with time. So the deaths of upper mass main sequence stars and supernovae. So now, actually, you know what? I'm going to keep sharing. Because what I want to talk about is this. Now, I really want to show you, my PowerPoint's not really working on this Chromebook, but just what should you write down here? Well, in a core of a main sequence star of a 20 solar mass, I'm showing it being bluish. The reason I have it written down here kind of in blue color, because the star is going to be blue. If it's 20 solar mass, it's going to be really bright, blindingly blue-white, blue. Hydrogen fusion. Now, this is not how to spell helium. I think Joe did this, our assistant, to honor Mike Healy, who's a friend of mine, but he's a Dodgers fan, so I'm really conflicted. But I've had to deal with this for, 30 years. So he's a good guy. He's a good guy. He's a little, yeah, I don't know. He's been, I don't know. Well, he's gone kind of the wrong direction being a Dodgers fan, but, he's a good guy. He's a good guy. So helium. Helium, that's not how to spell helium, but hydrogen fusion to helium, as is a main sequence star. Now, just maybe you can either write this down or remember. You're not going to have to know these numbers, but I want you to see the pattern. I want you to see the pattern here. The core temperature of this star on the main sequence is 70 million degrees. Now, the core temperature of the sun on the main sequence is only about 27 million degrees. Why is this so much higher in temperature? Because of the gravity. There's more gravity, more compression inside the star. So if it's a higher, more compression, more gravity, it's going to be hotter in the core, and it actually needs to be hotter to produce as many gamma rays for radiation pressure to hold the star up. Remember, this star is going to be wants to collapse due to gravity. There has to be a lot of radiation pressure from gamma rays. Fusion reaction has to go through very quickly. You have to have very high, intense fusion in order to keep the star up. Now, the core density. The density is the compactness. Now, the density of water is 1 gram per cubic centimeter. So that's the density of water. 5 grams per cubic centimeter is about the density of the Earth rocks. So it's pretty dense. It's not as dense as it could be. So a cupful of this, since it's 5 times denser than water, a cupful would weigh about 2.5 pounds. So it's a normal cupful of water weighs about half a pound if you ignore the cup. But this would be about 2.5 pounds. But look at this. This time spent fusing hydrogen in its core, 10 million years. So you know what's going to happen after 10 million years? It goes through its fuel very quickly. So after 10 million years, let me show you here. After 10 million years, this star here has run out of hydrogen. So what's left? Helium. Remember what's going to happen if there's mostly just helium in the core? Where there's going to be, kind of core collapse. The whole star is going to kind of start to collapse. There's not as many gamma rays. And then there's going to be shelf fusions that's going to cause the same kind of thing over here. Remember this? The same kind of thing over here. But instead of ending up over here, look where it ends up. It ends up over here. What's that region called again? That region is a supergiant. Those are supergiants. So these upper mass main sequence stars are going to end up as supergiants. Maybe over here, here. Some of these most massive ones are called hypergiants to begin with, and they don't even expand that much. They're pretty much dying as they're born because they're so massive. They don't change that much. So really, the supergiant region and also the very, very upper mass really kind of blends in over here, kind of like that. But I'm going to keep them separate for a test or for any homework or for any quiz or something like that. They're going to keep them separate. But it really kind of blends together here. So we're talking about now a star here. A star that is a 20 solar mass supergiant. Now, what color would that be? Look at that. Is that going to be red? No, look at that. It might be, who knows what that is, maybe an A star at this point. I mean, this was probably a B star right here. So remember red, you'd have to be way over here. Here are the reds, and there's orange and kind of yellowish white. So this might be a little bit bluish. So I'm going to show this supergiant on here. Let's take a look at this supergiant. There. So here is a 20 solar mass supergiant. I mean, it could be, I'm just making it blue. It may be more white or even yellowish. We'll just say this. Let's say it's 20 solar mass supergiant. Now, let's look at the core here. Remember, we have a core, the very center, where there was, helium and fusing, and then the helium eventually fuses to carbon, kind of like same as in a giant star. And remember, there are shelf fusions. Of course, there are all these shelf fusions going on, where we have hydrogen fusing to helium. You don't have to remember all this. There's helium to carbon, He to carbon eventually. And all of those are producing gamma rays. The core, we could do that. Gamma rays from the core, gamma rays from here, from the shell fusion, which are, you need a lot of gamma rays. Why? Because you have gravity bearing down, and this is 20 solar masses. It's not like the sun, which is 1 solar mass. There's a lot of gravity here. We'll write this, a lot of gravity wanting to compress this. So let's see what's going to go on here. Let's kind of move on with our a slide. Let's see what's going to happen. So now, what happens is this. Helium fuses into carbon for a while. And every time there's a lack of fusion or the fusion dies down, there's more compression of the core, so it keeps getting hotter. The core keeps getting hotter, so because the stages from one fusion to another, there's core collapse. So the core keeps collapsing, you're getting hotter. Look at this, the core temperature. Now you don't have to, do you have to remember, maybe you remember helium fusing to carbon, that might be a good thing to know, but do you have to worry about that it's 320 million degrees Fahrenheit in the core? No, but just see that it keeps getting hotter. It keeps getting hotter. The density now is 900 grams per cubic centimeter of the core. It would be like a cup full of water. Instead of replace the water, it's with something that's 450 pounds. I don't know what's 450 pounds. Like a bear. Don't do this to a bear. But like a good-sized bear, putting 450 pounds, medium-sized bear in a cup. That's dense. You couldn't pick up with one hand. I don't know. I couldn't pick it up with 450 pounds. I mean, very few people could actually pick that up at all. That's how dense this core is. Very dense gas, still gas. But look, the helium fusion to carbon, it only lasts for about 1 million years. Each 60, notice what's going on here. Hydrogen to helium in the star lasted for about 10 million years. This helium to carbon only lasted for 1 million years. Each successive fusion doesn't last as long as the previous fusion because it's not as efficient. Hydrogen fusion is the most efficient. And then the fusions after that are not as efficient. So you have to fuse more of your gas to get the same amount of energy. And you need a lot of energy to balance the star because there's a lot of gravity bearing down on it. So after 1 million years, helium runs out. But what's left in the core? Yeah, it's been fusing into carbon all this time. So let's see what's happening in the core at this point. The core is now carbon. So let's go back to our picture here. I don't know if you have the luxury of erasing, but I'm going to erase. Now, let's look at this core. I'll put a C there. Carbon. C for carbon. But around the core, now if there's not much fusion going on in the core is going to collapse. So the core starts to collapse and then get hotter. But you know what's happening around here? Look at this. It's kind of neat. We have a region out over here, a region of hydrogen fusing into helium, and now a region of helium fusing into carbon, not from the core, but from around the core. Remember what that's called? Shell fusion. So shell fusion is going furiously to produce enough gamma rays to provide enough radiation pressure to keep this star from collapsing due to gravity. It needs a lot of radiation pressure. Well, remember at this point when you had a giant, let's come back to this. This is kind of like when we had a giant star right here. At this point, something happened to the star. What happened? Remember the burp, the cosmic burp? The planetary nebula stage happened and it lost its envelope. Guess what? This time there's no planetary nebula stage. So there's no planetary nebula stage. Why? How come it happened for a star like the sun, but not this star? Here's why. Look, a lot of gravity. There's so much gravity that there's not enough radiation pressure to push off the envelope. So what's going to happen is more successive things. This is not the end stage. It keeps going. So what's going to happen? The core keeps collapsing. So as the gravity's compressing the thing and there's not much fusion going on in the core, just in the shell fusion, a carbon core collapses, and eventually, you know what carbon will do? Carbon will fuse. So let's see what's going to happen here. Carbon fuses into neon and oxygen. You don't have to remember all these successive things. I have them written down here. That's how I remember them. I can't remember them all the time. But carbon fuses into neon and oxygen. Hot enough for carbon to fuse. Look at the temperature here. 900 million degrees Fahrenheit. Just see, the temperature keeps getting higher. the core density is 150,000 grams per cubic centimeter, 150,000 times denser than water. It would be like 75,000 pounds in a cup. Now, I don't know what 75,000 pounds, like I'm trying to think of what's 75,000 pounds, like a whale? Like a whale. A whale in a cup? Don't do that to a whale. So imagine, that's dense. That's dense. So the density keeps getting higher, but the temperature keeps getting higher, the compactness, the density keeps getting higher. And look, time spent fusing carbon in its core, about 1,000 years. Well, only 1,000 years. Now you say, well, that's still long. But compared to talking about the sun, like when we talk about the sun, things lasting millions, billions of years, 1,000 years is nothing. But after 1,000 years, what does it run out of in the core? Carbon. What's left? Neon and oxygen. So what happens? The core starts collapsing until actually oxygen starts fusing into silicon. At this point, the core temperature is about 2.7 billion degrees Fahrenheit. The core density, 10 million grams per cubic centimeter. It would be like 5 million pounds in a cupful. I mean, that's like 5 million pounds in a cupful. That's like something like I don't know, imagine a cruise ship compressed into a cup. Something like that. I don't know how to think, it might be it could be something like that. A cruise ship compressed into a cup. That's crazy. But the time spent fusing oxygen in its core. And there's other fusions going on. There's sulfur, there's magnesium. I'm just hitting the highlights here. There's other elements being formed here from these fusions. The time spent fusing oxygen in its core, 1 to 2 years. That's crazy. That's like, 1 to 2 years is something everybody kind of has a feeling for. But after 1 to 2 years, do you know what runs out in the core? Oxygen. What's left? Silicon. And then this core collapses. And what happens is the core gets hot enough for silicon to fuse into iron. And this goes on. Now look at this. This is ridiculous. 6.5 billion degrees Fahrenheit. Yeah, it's something we encounter every day. You can get now. It's ridiculous. The core density, 100 million grams per cubic centimeter. Oh, this is like, I don't know, 50 million pounds. 50 million pounds in a cup. I don't even know what that is. It's like something like 30 aircraft carriers, or maybe more, 100 aircraft carriers compressed into a cup. It's crazy, the density. The time spent fusing silicon in its core is 1 day. After a day, what's gone? Silicon. What's left? Iron. Now, wow, we got to talk. We got to talk now. Because look at this. Let's look at what's going on here. We're going to end up with a core of iron, dense iron gas eventually. And let's see what this is going to look like. Again, my picture is not really representative of what things look like, but you can make a much better one than me. So the core now, it's small. It's like this. We're going to say this is a Fe, which is iron, core. Now, iron gas, dense iron gas, very compressed though. So eventually the core is dense iron gas. But you know what's going on around the core? There's all these regions. What do we call it that are fusing? What do we call this again? Shell fusion. So in the outer region, we have hydrogen fusing into helium, and then there's helium fusing into carbon, and carbon into neon and oxygen, and so on. So they say, look, what kind of like vegetable does this remind you of? Slicing it and kind of looking like this. They say it kind of resembles an onion. Not really that you're going to peel off layers like you can with an onion. You could peel off, these layers of an onion. There's really no layers to peel. It's just different things happening in different regions. And all of these shell fusions are producing gamma rays, right? And these gamma rays are needed. Why are they needed? Because gravity wants to collapse this thing. Gravity wants to compress this. So it really needs to do this. Otherwise, you see, this can't go forever. But there's a problem now. This iron core starts collapsing and heating up. And watch this. The iron actually can start to fuse. Now, iron can fuse into every heavier element when the iron core starts fusing. The iron fuses into gold, silver, uranium. It fuses into everything heavier than iron, everything. All the gold, all the silver that we have was from something like this happening. But wait a second here. What's the problem? Well, there's a problem when iron starts fusing. Let me show you this little bit of a table here. Now, you don't have to draw this. This is something, it's going to look like an HR diagram. I know you guys have probably been trained by now. It's not an HR diagram. This is a graph of what I'm going to say down here is an element. It's like element. Let's say hydrogen is here. Here's helium. Here is iron. Here is uranium. And again, if you don't want to write this, you don't have to. I'm going to write something over here called binding energy. Binding, energy, which means the energy required to hold a nucleus together. Now let me show you this kind of interesting graph. Well, I think it's interesting. You may hate it. Watch this. What this shows is that if you fuse hydrogen to helium, a helium nucleus does not require as much energy to hold it together, so energy is released. When helium fuses into, remember what helium fuses into? Carbon, energy is released. Carbon fuses into neon and oxygen, energy is released. If you go to uranium, uranium doesn't really, well, you remember what it undergoes fission? When it becomes smaller nuclei, energy is released. Iron nucleus is very stable. So we can say this, that a iron nucleus is very stable. Which means that, yeah, you can start fusing iron into heavier elements, but do you see what's going on here? Energy is not being released. Energy is being absorbed. So we say this. If you want to write something down from this, write this down. Iron fusion absorbs energy. Absorbs energy. Now, let's think about what's going to happen. It's like this. If the iron fusion is going to absorb energy, where's it getting energy to absorb? So this is going to start taking in energy instead of liberating energy. Where is there energy around it? Energy as far as gamma rays. Aren't there gamma rays around it? So it starts taking in gamma rays. Well, is there a problem with that? Because what are these gamma rays doing? Aren't they being used to hold up the star and keeping gravity from collapsing it? What if the gamma rays, a lot of these gamma rays that are being used to support the star are going into the core now? You know what it's like? It's like someone holding, let's imagine holding up your friend, like with your hands raised high, holding up your friend, and someone pulls down your arms. What happens to your friend? Yeah, it's not good. Your friend goes down. Your friend collapses or goes down. What about standing on an empty, like, water can or something like that, or a soda can, and someone pinches in the sides? What happens? It gets crushed. So, look what's going to happen here. Look what's going to happen. I'll show you. I'll try to show you. So again, iron fusion, go every heavier element, gold, silver, copper, nickel, uranium, all that stuff that you know, some of it you know well, like gold, if you want to know it well, like silver. Well, here's where you get it, from iron fusion. The core temperature, 350 billion degrees Fahrenheit, ridiculous. The core density, 200 trillion grams per cubic centimeter. That's probably, you know what that's like? I don't know what it is. It's probably hundreds of thousands of aircraft carriers compressed into a cup. Ridiculous density crazy. The time spent fusing iron in its core, a fraction of a second. Within a fraction of a second. Now, oh, I don't know if I can show. Yeah, it's not going to. Is it working here? No, of course not. It's not working. But I'm going to try to show it. And I'll try to dig a video for you to show this too. Within a fraction of a second. Now, the whole thing doesn't go in a fraction of a second. There's an implosion within a fraction of a second. All these layers start falling in on the core. And then there's a rebound. So there's this. So what happens is kind of like your friend falling when you can't carry your friend, or the Coke can compressing inward. There is an implosion of the star. I mean, not the whole star, but there's like a shudder. It kind of like compresses inward, followed by an incredible explosion, which is called a type 2 supernova. A type 2 supernova, the explosion of a supergiant. Now, the supernova does not take place instantly. What happens is this collapse is almost instant. But things can't go faster than light. So there's these layers fall in, and then they rebound off the core. Now, there are different ideas about what happens here. There are different ideas. One idea is that there's a rebound off the core, and within a few hours, there's this shock wave that blows the star to bits. That's one idea. Another idea is this, that because computer models, they don't show as violent as these are. These things are incredibly violent. We're going to talk about that. Incredibly powerful, incredibly violent. Models, simulations don't show how violent they really are. So we're thinking there's something we're missing. There's another idea what's going on here to create these supernovae. When everything is fusing at the instant, remember a little particle that's created during fusion? That's very hard to detect, that we have detected, but not that many of them? Neutrinos. Neutrinos. A lot of scientists, astronomers think at the instant of the supernova, or of this implosion, there are so many neutrinos produced, even more than normal, which is a lot, that neutrinos help explode the star. That interactions with neutrinos and the interior of the star help blow up the star. Now remember, neutrinos don't really interact with matter very easily, but what must be true about the density of the matter for neutrinos to interact more? High density. Didn't we say this was trillions of grams per cubic centimeter? You think that's high density? Yeah, that's high density. So more neutrinos can interact. Now, how would we test this theory that neutrinos help explode a star, a dying star, or cause a supernova? Well, don't we have these neutrino detectors that detect neutrinos? Yeah. Well, we did see a supernova in 1987, and we're going to talk about this in another galaxy. And before we saw the light from the supernova, some hours before, a detector, a supernova detector, a water tank, that was normally detecting about 1 or 2 a day, detected 11 of them in a short period of time. And then we saw the supernova. Well, wait a second here. Does that mean these neutrinos are traveling faster than light? And people thought, oh, that means that if we detect them first before the light, they're traveling faster than light. But no, here's what we have to think about. Neutrinos almost go the speed of light. If you have any mass at all, which we think they might have a little bit, they can't go the speed of light, but they can go close. And the neutrinos we detected are not the ones that helped explode the star. They are the ones that got away before the star exploded. They had a head start. And if they had a head start and they're almost going the speed of light, they can get to us a little bit before the light. So, yeah, neutrinos might play, a big role in this. But there are other ideas. They say this core actually might become a black hole. And all this stuff starts falling into the black hole within this instant, if it's really close. And it creates these jets of energy that go 180 degrees from each other and blow up the star. We have evidence for something like that. Who knows? We can't even see the stars, so we can't really tell what it is. But we do see these supernovae, not that often. But it's puzzling. It is. They're really neat things, these supernovae. So I don't know. The star's going to blow. I don't even want to do it the injustice of trying to show my picture blow up here because I can't really replicate it. I'm going to post some a video of it, a video of a star blowing up. I can't do it. I mean, I don't know how to even do it here. Let's just go back to our slides. All right, so I wish I could show you. This is not working on here. All the heavy, at the time of a supernova, at the instant of this, and within, I mean, every heavy element is created. Everything in your body, I mean, maybe not, let's say the hydrogen, which could have been their original hydrogen, the atoms in your body, the gold, the silver, I mean, yeah, a little bit of gold, a little bit of, magnesium, iron, all that stuff in your body, all these heavy elements, and if it wasn't created in a supernova, it was created maybe in a planetary nebula, right, as a giant died. So if you trace back the atoms in your body, you know where they come from? The atoms in your body come from the stars. You say, well, no, they come from food I ate. Oh, yeah, okay. Where did the food come from? Oh, the food came from the earth. Oh, okay. Where did the earth come from? The earth came from material that didn't form into the sun. Where did that come from? Came from the stars. So a supernova is, this is pretty powerful. It creates life eventually. It creates planets. If you're too close to a supernova, within 70 light years, you're toast. But so, you just don't want to be close. Sometimes you may not have a choice. I think we're okay. We'll talk about that. But if you trace back, again, all the atoms in your body, where do they come from? Oh, they came from the depths of stars. So some people go out there and look at the ocean and feel a connection. Well, that kind of makes sense. Life came from the ocean originally. But before that, life came from the stars. So if you think about the stars, and you're made of star stuff, as Carl Sagan would say, isn't it like the stars thinking about themselves? I mean, think about that. If you feel a connection with the stars up there, there's a good reason. They are your relatives, these stars. Without the stars, without them dying, we wouldn't be here. We wouldn't have planets. We wouldn't have us. My dad knew this. He wrote our text, which I didn't have you buy, but I want to read you. There's an excerpt from it that my dad talking about this, and he said this. This is on the back. It's in the book. If you ever want to buy the book, or just take a look at the book. He says, here's what my dad says: I believe there is a fundamental reason why we look at the sky with wonder and longing, for the same reason that we stand hour after hour gazing at the distant swell of the open ocean. There is something like an ancient wisdom encoded and tucked away in our DNA that knows its point of origin as surely as a salmonid knows its creek. Intellectually, we may not want to return there, but the genes know and long for their origins, their home in the salt's depths. But if the seas are our immediate source, the penultimate source is certainly the heavens. The spectacular truth is, and this is something that our DNA has known all along, the very atoms of our body, the iron, calcium, phosphorus, carbon, nitrogen, oxygen, and on, were initially forged in long dead stars. This is why, when you stand outside under a moonless country sky, you feel some ineffable tugging at your innards. Now, I don't know if you feel this, but some of you might, and if you do, that may be why. That may be why. So now, let's see what else we have here. Let's talk about this. So, all right, let's just talk a little bit about this. A type 2 supernova. Now, don't write any of the, if you only write down what I tell you to write down. This should come on slowly, but in this program right now, on this Chromebook, it's not doing it. Just think about this, and I'll tell you what to write down, all right? Don't write all this down. I'll tell you what to write down. A type 2 supernova, and we'll talk about other types too, releases more energy in 1 second than the sun does in its entire lifetime. I mean, that's ridiculous. I mean, think about the sun's lifetime, 10 billion, 12 billion years. All the energy is released from it, not just the energy that hits Earth, but the energy that's lost into space. In a supernova, in 1 second, there's more energy released. If you can't believe that, you can't fathom that, you're perfectly fine. That's crazy. So if you want to write down something, you can say you get an incredible amount of energy. That's good enough. It can appear 20 magnitudes or 1,000,000 times the luminosity brighter for a few days than the star appeared beforehand. So it's all of a sudden something like when you see Venus in the sky, which is really a planet. So if you see Venus, and it gets as bright as the sun for a few days, there could be, I mean, if a star goes supernova, it could be almost like another sun in the sky, another star, not quite as bright as the sun, but it could be easily seen during the day. So 20 magnitudes, that's crazy. So if you want to write something down for the second part of the year, you can say it gets a lot brighter. Now also think about this, because even though it's a lot brighter, it releases only 1/100th of 1% of its energy in visible light. The rest are in these high-speed protons and electrons called cosmic rays, other types of EMR and neutrinos, a lot of gamma rays, a lot of X-rays. So what you see as visible light, which is blinding enough, I mean, it's crazy. That's only 1/100th of a percent of its energy. So that's another reason you don't want to be around these things. Not only are they blinding to your eyes, but they can produce a lot, an incredible amount of other types of EMR. So now, something else. Remember we said a supernova in the distance, a very, very far away, might give a nebula a push it needs to stimulate star formation? So yeah, maybe write down it could help stars forming. It could help stars forming. So that's another thing it can do. I mean, we think. And again, also, it creates all these heavy elements and spreads them into space to create planets and life. Now, again, they could destroy, supernova would destroy your planet if you're within 70 light years, but hey, if there's no life it's destroying, it's really only creating possibilities of life, like heavy elements. But I'm sure some supernovae in the past have led to the demise of civilizations. I mean, that's just what I'm thinking. Now, there's also these cosmic rays, these high-speed protons and electrons. They say they might help in evolution. They cause mutations of cells, which could be bad. You get too much mutation. But if there's just a little bit of mutation and adaptability, there is evolution. So look at this. Supernovae, they create heavy elements. They may create stars to be formed. They produce heavy, they maybe produce these cosmic rays that cause evolution. They're like the governors of the universe. Without supernovae, we're not here to talk about them. There may not be the universe as we know it without these stars blowing up. That's pretty exciting. Now, look at this. I wanted to kind of hide this from you. Some historical supernovae in our galaxy. You don't have to know. Actually, look, they're happening about every 300 years or so, on average. About every 300 years, we see them. In 1006, we saw one. In 1054, we saw one. We're going to talk about that one. There's a remnant of that. In 1572, we saw one. In 1604. And finally, we got the telescope in 1609. That's when it was invented. And we haven't seen any in our galaxy since. What? That's crazy. What's going on here? That's not fair. These are all naked eye ones where there have been drawing Native Americans that are that have these cliff dwellings and kind of like these carved into a rock. How it looked like. There's a lot of Chinese and Arabic recordings of these. There weren't any European ones in certain times because of the Dark Ages. You weren't really, according to the church, supposed to see anything new up there. So earlier, if you go back to 1054, and if you're in maybe Europe at the time and you reported something new in the sky, you're in trouble with the church. So they, of course, saw it, but they kept it to themselves. But at least we have, other like the Chinese, Arabic, Native Americans, Japanese records. They didn't keep it to themselves. Yeah, they were not afraid as much as some other people to say they saw something. So then the telescope. Now, does that mean they're only happening about every 300 years? Well, no. Let's take a look at this. Let me show you. Let me show you this. Let me show you why we don't see them that often. They might be happening more than that. So let's come back to this. Let's show our galaxy. The Milky Way here, kind of an edge on view, kind of like that. So there's our galaxy. And we are somewhere there. What if there's a supernova that takes place here? Do we see it? No. Why? There's too much dust in the way. We can't see all the way there. What if there's a supernova here? No, we don't see it. No, no, no. No, 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 no. I don't know, maybe yes. We only see about this much of our galaxy. So we only see 1 in 10 supernovae on average. So we think they happen about every 30 years, even though they happen every let's say 30 to 100 years. If they happen every 30 to 100 years, and we only see about 1 in 10, we're only seeing them every, like, you know, let's say we're seeing about every 300 years. I mean, we might see 1 in 5, but probably not, probably 1 in 10. So we see them on average about every 300 years or so in our galaxy, but we think in other galaxies we might see them every 30 years. So we don't see them much in our galaxy. We see more in other galaxies. Why? Why do we see more in other galaxies? Because we get a better view of other galaxies, like being in a swimming pool filled with people. Remember when we used to be able to go to swimming pools and go in with other people? There would be, I mean, you could go down in the water and not even see your friend who's in the pool. You say, where's my friend? I can't see your friend. It's filled with people. Your friend might be 20 feet away from you, 10 feet, you can't see your friend. But you look straight up out of the water and you see a 747 or a jet 5 miles away. Say, I saw something 5 miles away. I can't see my friend 10 feet away because there's too much stuff. But if we look out of our galaxy and see other galaxies like the Large Magellanic Cloud, we get almost a full view of it, at least half of it. So if one blows up in the Large Magellanic Cloud, we probably have a 1 in 2 chance of seeing it. So we see them more in other galaxies than we do in our own. And we have automated telescopes finding these like all the time in other galaxies, but mostly very far away, which is kind of good because you don't want them to be close, but it's also kind of bad because you want to study them. And if they're too far away, you really can't study something from that far. So you want them kind of close to study. You don't want them too close. You don't want them within 70 light years. You want them farther than that. But if they're too far, you can't see them in our galaxy. And if they're in another galaxy, you can't see them very well. That's the problem. But in 1987, one blew up in the Large Magellanic Cloud. Does that mean we saw it in 1987? Did it happen in 1987? No, because that's 170,000. Oh, there it is. I saw the picture here. Large Magellanic Cloud is right over here. Sorry. There's a Large Magellanic Cloud. It's 170,000 light years away. We had to wait 170,000 years to see the explosion after it happened. So we're seeing it. We saw it back in time. I'll show you some pictures of it. So just remember, we see them in other galaxies more often than we see them in our own. So now, let's see here. Supernova Remnants. I'd like you to remember Supernova Remnants. Supernova Remnants is what happens after the supernova. It's the remains after the supernova of supergiant stars. Just like a planetary nebula is the remains of a giant star dying, a supernova remnant is the remains of a supernova of a supergiant star. There's a supernova remnant. Here's one. Well, there's not much of a remnant. Here's a galaxy called the Black Eye. If someone like punches someone and gives them a black eye galaxy, and there's a supernova going off. Look at that. Happening millions of years ago, but yeah, it takes that amount of time to reach us. Now, the most famous supernova remnant. Here's Orion. Talk about Orion. There's the belt, the shoulders, Cetus in the winter, Taurus the bull, and there's the Pleiades, the seven sisters, Subaru, right over here, next to one of the horns of the bull. Now, the bull's face is here. There's Aldebaran. Here's one horn. There's another horn right there. There is. And again, right here's Orion, and this object is right there. Hold on here. Yeah, it's ruined here. It's ruined. It's the Crab Nebula. In the real PowerPoint, this does not come on yet. Okay, hold on here. Let me go forward. Let me see if I get a picture of it. Well, yeah, here's a decent picture. There. This is a pretty good picture of it. This is the Crab Nebula. And I would like you to know this as a supernova. The one supernova remnant I want you to remember is the Crab Nebula. This is from the explosion of 1054. Actually happened on July 4th. We're coming up on the anniversary in about a week and well, depending on when you're taking this class, you may be coming up on the anniversary of it. But so yeah, on July 4th, the 4th of July. Well, it's not. I guess they didn't celebrate it then like we do now. But the Crab Nebula. Now, let me go back here. And that's the remnant. All these a supernova remnant is more chaotic, more wispy. It's like more violent than a planetary nebula. Now, I don't know if you never heard of the crazy crab, but I might as well tell you about this crazy crab. In 1984, this would be the Giants, San Francisco Giants, my favorite team. I mean, I love the Warriors, basketball. I love the San Francisco Giants. All right. I actually love every sports team for the most part, except the Dodgers. I even don't mind the Lakers. I mean, the Dodgers, no, I don't even bring that up. But okay, let's go back to this. The crazy crab. Crazy crab was the Giants mascot in 1984 for 1 year. Everybody hated it. This is when the Giants were terrible. They were losing like 100 games. This was before Will Clark and Robbie Thompson and Kevin Mitchell. And this crab would run across the field like in the seventh inning. People would pelt it. Now, luckily, there weren't many people there. There were like, 2,000 people there. But people would pelt this thing. They hated it. So this crab would run across the field, run for its life, pretty much. And it would disappear down in the clubhouse, down the line. This was at Candlestick Park. Yeah, this is before AT&T Park, or Oracle. I still call it AT&T. So this crab, everybody hated this crab. I mean, its own fans hated the crab. I mean, if your team is just pathetic and terrible, you don't want to see things dancing on the field. I mean, it's insulting. So this crab only lasted for about a year. And if you go, now I know what happened to it. I might as well tell you. If you go to AT&T Park, and some of you have, if you go to the center field, now I don't have my slide in this PowerPoint. There is in center field, beyond center field, the eating area. There's the Crazy Crab Shack. They sell crab sandwiches there that are $17. I've never had one of those, but there are people that have had it. The $17 is it's the Crazy Crab Shack. You know why the sandwiches are so expensive? It's because there's a limited supply. That's what happened to this crab. There's only so much crab to go. And go there and check it out. If it's still, I mean, there may not be any crab left, but at least you can go check it out. I think it's going to kind of go out of business when there's no more crab, which is okay with me. But the Crazy Crab Shack, All right. Something is left in the Crab Nebula. There's something moving. We're going to talk about it. Not all of the stars blown up. There's something left there. We will talk about it. Here's a close-up of the very center of the Crab Nebula. Here's another supernova remnant. Here's the Veil Nebula. You don't have to write these down. Another supernova remnant. This gas is moving out through space at tens and tens of miles per second, very fast. And over time, it spreads out. And it doesn't resemble this thing it did right after it blew up. This one looked like, it kind of looks like a jellyfish, but someone once said it looks like the ghosts that chase Pac-Man. Kind of looks like that, doesn't it? It's kind of a ghostly, the supernova remnants are just beautiful. Here's the one from Supernova 1987, actually in the Large Magellanic Cloud, beforehand and after. Here's the Supernova 1987 picture from 170,000 light years. Look at that. We're getting a pretty good shot. There it is. Now, these are foreground stars, not part of it. But here is the Supernova Explosion. Here's where we think it's mixing with other gases. And they think that, I mean, this is after a while of expansion. And the heaviest elements, they say, is here, where the heaviest, where iron gas and nickel gas and gold gas is going to eventually form into solid material when it cools and goes into planets. And eventually you have the stuff. Now, we're not going to get that stuff here. But the gold we have here is from a star that died before, many stars that died before. All these heavy elements. Now, this is from 170,000 light years. Look at that. And here's a progression. From 1994 to 2003, about 10 years, and you can see these changes. Wouldn't it be nice to be closer to this, to see this in more detail? This was a Hubble Space Telescope shot. Now, not too close, but closer. Not too close, though. Now, what do you need to know about this? Supernova 2006 GY. Well, don't have to worry about it happening in 2006. This is an illustration of it. This was a visual light picture, a visual light from a telescope. Here was a Chandra X-ray vision of it, and it's two lobes, which kind of gives the idea that a black hole caused this one. It's the second most energetic supernova ever seen. It's 100 times brighter than a normal supernova. Now, supernovas are bright enough. This is 100 times brighter. It's in a galaxy 240 million light years away. You don't have to know that. The star that blew up, we think, was one of these called hypergiants, a very, very massive supergiant, which actually didn't even become a super. It was born as a supergiant. It was in the very, very upper part of the main sequence. It was kind of a supergiant to begin with. They say it might have been up to 150 solar masses. And when these go, the supernovae are called hypernovae. Here's the one thing I want you to know. The most energetic type of supernovae are called hypernovae from these hypergiants. Again, I'm going to say it again. I want you to know it. The most energetic type of supernovae are called hypernovae. You do not want one of these around you. Actually, 70 light years from this is not safe enough. 200 light years not safe enough. I don't know what's safe enough. But if you have a hypergiant relatively close to you, you better get out of your star system and go very far away. It might not be easy. It'd be hard for us to do that right now. So yeah, a hypergiant going hypernovae, you better be far away. 70 light years is not enough. Now look at this one. This is in our galaxy. It kind of looks like it's blowing up already, but it's actually undergoing something called mass loss. We're going to talk about that. There are bubbles of mass being ejected from this star, we think, before it blows up. It is a supergiant or hypergiant, up to 120 solar masses. They say it could go supernova soon, within 100,000 years. Actually, it's 7,500 light years away. If it goes supernova today, we still have to wait 7,500 years. Now, wait a second here. Look at this. Its apparent magnitude is 6.2 now, which you couldn't even see with the naked eye, unless you have really good eyesight. But in 1843, its apparent magnitude was -1. It was the second brightest star in the night sky, just about 170 years ago. It was the second brightest star in the night sky, now you can't even see it. Things are happening with this star. Things are changing. It's bubbling off this mass. Maybe it's kind of in a lull. It might have gone supernova now, and we don't even know. They even thought Betelgeuse, the star Betelgeuse, was about ready to go supernova. It's going to. And Betelgeuse is about 600 light years away. It decreased in magnitude quite a bit, Betelgeuse. We can talk about that. But then it's kind of like it came back again. So something's going on with Betelgeuse. Now, the peak luminosity of this thing, this Eta Carinae, was about 4 million times the luminosity of the sun. Imagine the sun being 4 million times brighter. You don't want to imagine that. So, but this is 7,500 light years. What if this does go? This would be a hypernova. Are we safe enough? It's 7,500 light years away. I think we are. I don't know. I'm not an expert. I mean, I don't know half the stuff I'm talking about. I should have told you that earlier. I try to report what's correct, but I could make mistakes. I don't know. I don't know if we're safe enough. Maybe we should not even think about that. Let's go on. Youngest supernova known. All right, forget about it. Think about this one. If you don't think about ones that might get you, think about like a young one, a nice friendly one here, a young supernova, the youngest one. Don't even write this down. I'm just trying to get your mind onto something else. All right, well, that's it. That is it. That is it for today. That is supernovae. So hopefully you got something out of this. If not, well, I'm sorry.